Well, over the years, we've been learning more and more about DNA. This stuff that's in everything, including ourselves, of course. We know kind of what it looks like. It's often described visually as a double helix. But what does it sound like? It's possible it sounds a little bit like this. That's a musical representation of DNA that's been made by our next guest. Mark Temple is a lecturer in molecular biology at Western Sydney University. You might also know him as the drummer from that great Sydney band, the Hummingbirds. G'day, Mark.
Hey, Cassie, how are you?
Well, I've got to break the news. I don't think you're going to have a bestseller. I don't think you're going to top the charts with that, but it's very interesting.
Yeah, that was never the intention. What you heard then was an artificial bit of DNA, just a run of G bases driving an audio sequence. So I notice how I use the term audio rather than music. It's an important distinction.
Yes. So I know very little about DNA, except I have seen that film Gattaca.
Yeah.
And I know that the title
GATC, or whatever the letters.
So those are the letters that are the elements found in DNA, and it's just the sequence of those.
Absolutely.
Right.
So DNA is a long string-like molecule. It's billions of base pairs long, so it's incredibly long, but it's only made up of 4 individual bases, which are your G's, A's, T's, and C's. So the question is, there's a lot of information there. How do you read that information?
So a earthworm might have a sort of, shortish sequence, and a Tyrannosaurus Rex would have an enormous sequence.
Well, actually, the size of the genome is sometimes not related to the size of the organism. Like, I think rice plants have a much bigger genome than humans.
Oh, really?
Yeah. So it's not, size does matter, but in some instances, it's...
Yeah. All right. So why have you embarked on this?
I embarked on it because I have a knowledge base in music and a knowledge base in molecular biology. So I was looking for a niche of overlap between the two where I could apply my skill set. And I realized that sonification was a useful procedure, and it's used in various disciplines to use audio to identify and analyze a phenomena. So I thought the DNA was the perfect thing to sonify for me.
Give us an example of another use of sonification, not the one that you're doing, that we might understand.
Yes, so some people try and sonify stock market data, and there's been a lot of attempts at doing that, and to identify trends.
So you might be like sitting at your desk, mucking around on social media with a musical analog,
and suddenly you hear a blip noise in the background that goes, "Ooh, what's happening?" And you go and pay attention to the screen.
Or if it gets higher, you might think stocks are going up. Or...
Yeah. The first example I could find of sonification dates back to the very first computers. And this computer had something called a hooter. And when the computer needed assistance or got, something was going wrong, the hooter would make a noise. So a single tone would come out. So the very first computers back in the 40s or whenever it was, had a way to sonify some information. I was just trying to sonify information in modern day computers. So
it's actually a great sense that we have that we may not be utilising in kind of useful ways. It makes me think of, I had for a while a German car. Now, actually, I think it was Swedish.
An Ovlov.
There you go.
That's Volvo backwards, by the way.
Right. I mean, it was a sort of high-end car that reached the end of its life by the time I got it. But it had this very clear use of sonification for things like reversing and for indicating different things. And I became quite reliant on just using the sounds to park. And then when I got another car, it offered me the screen where I could see reversing, and that was much more difficult for me than the sound. So I can kind of understand the use of this.
Also like Geiger counters. They start crackling really loudly when they detect high levels of radiation.
And we instantly know what that means.
Yeah. Or vacuum cleaners, they just annoy us and drive us crazy.
Yeah, and you know when they're blocked because they make a different noise.
That's right.
Yeah,
That's right.
Interesting. Okay, so that example that we just heard then, that's a very basic one. Let's hear another example of the sonification of DNA. Now, there's a couple more tones in there. What are we hearing?
Absolutely. So the first thing you heard was a sequence that I made, just a bunch of Gs. The second one we played then is actually from something called a human telomere, which is at the ends of our chromosomes. So all our chromosomes have that sequence in them. And it's a 6 base pair repeat. So it goes da-da-da-da-da-da, which is 6, da-da-da-da-da-da-da-da-da-da-da-da-da. And when there's a mutation in that sequence, the sonification changes and the pattern, the repetitive pattern switches from one pattern to another. And it's really clear to your ear when it happens. But if you look at the sequence by eye and look for the mutation, you can't see it. It's really hard to see. So I thought that was a good example of how sonification has its advantages.
And you've chosen the sounds arbitrarily just because you're a musician and you've chosen ones that appeal to you?
Yeah, well, I wanted to use sounds that have a fast attack because the music's so fast, it's going da-da-da-da-da-da-da. You want a sound that starts with a clear tone. So the piano is quite percussive. So those sounds you can hear clearly when you play them quickly. I could have used bleeps and crackles and bops and weird noises, but I think that's grating to the ear. So I chose sounds which are familiar, such as music instruments, but I don't want to make too much confusion with music within the science community because it's not about music, it's about audio and sonification. But the thing that I didn't anticipate is that people have cottoned on to the sound of the audio, and that's generated a lot of interest in the process. So it's become actually a good learning tool and a good way to talk about the concepts. So it's been a win-win in that sense.
So you're, the byproduct is the art, and that's also what's engaged people.
Yeah, absolutely. And had I known that at the time, I would have been strategic and planned it that way. But I wasn't. It's just fortuitous. So,
tell us about some more applications you could imagine for this. Are you imagining it's just in labs that people would be listening to it?
Well,
or maybe, could we, I don't know, could we wear a device that we were listening to ourselves and we'd eventually be able to understand little fluctuations in our, hormones? Or
Well, currently it's designed to run in nerdy computer science databases. But sequencing is becoming more and more common. So rather than it costing $1 billion and taking 10 years to sequence a genome, as it did 15 years ago, now we can sequence our own genomes for less than $1,000 in less than a week. And it's only going to get cheaper. So we're going to have access to our genome sequences at some point. I don't know whether people would be then interested in engaging with their information in some way. It's not a way that's particularly useful for identifying diseases for themselves, but it does engage them in the process. And if you understand how the audio is generated, then it tells you something about how the cell processes that DNA to make proteins, because the rules I've used are based on biological rules. If you delve in a bit deeper, you start to understand that the pattern of notes is based on biological rules of how a protein's made.
So it's far easier for some people to process this information by looking at a sheer waveform or a DNA sequence on a graph or a page or however you look at it. It's hard to kind of to process. So for some people, they're going to understand the concept. So it's a teaching tool.
It is. It works in that domain. And if I massage the audio in a certain way, which I might do as a second follow-up publication, you can actually use it as generative music. And if that's soothing and you've got a disease and you've got your genome sequenced, you can actually listen to it. And I think that's a nice outcome. It's the idea of an unanticipated consequence of what you've done is that you've got something you can listen to as well. And it might be interesting to see how we can generate those audios.
Let's hear one more. This one's a little bit more complex.
Oh, yeah.
What is this? What is going on in this one?
Okay, This one, the piano is dominating. So that's telling me straight away that a piano sequence by itself is called an open reading frame. So it's a gene sequence, because gene sequences aren't interrupted by stop codons. And I use stop codons to stop the audio. So
within your little scheme that you've devised, a piano means...
So a bit of background information for people who don't have much information on biology is that at the start of a gene, there's a particular 3 letters, those G's, C's, and A's. It's called an ATG, and that's a start. And at the end of a gene is another 3 letters, TGA. So I've sonified those particular base pairs, those codons, as certain sounds, and they stop and start the audio. On that one there, because it's not going da-da-da-da-da-da-da, it's going ding, 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 ding. It indicates an open reading frame to me, which means it could be a gene sequence. Because often we don't know what the sequence is we're looking at in science.
Aha, I understand.
Good, that's pretty good.
So you'll be talking to Dr. Karl about this for Science Week.
I will. One of the, getting back to these unintended consequences, is that I got invited last year to play some music based on the idea of sonification. And I was quite surprised by that, but I engaged with it with Paul Smith from University of New England and Trisha from the Clouds back then. Uh-huh. And we played music inspired by genomic DNA, and we've been invited back again this year. This time it's with Dr. Karl. So Dr. Karl's going to talk about his book. I forget what it's called, Life, the Universe and Everything, something like that. And that'll be fantastic. And then afterwards, we're going to get up on stage with Paul and Peter Felix on bass, and we're going to play more audio inspired by the sound of DNA.
What's the band called? I hope you've got some.
I've been trying to think of a band name. I was thinking of the plastic exploding inevitable gene expression experience, or something along those lines. Something that no one will ever remember.
Oh, I'm sure you'll get a few suggestions from our listeners. Well, look, fantastic work. Totally perplexing and delightful as well at the same time. And kooky.
Thank you. I think it's really kooky. We're a couple of kooks.
Oh, yeah. Mark Temple is our guest. He's a lecturer in molecular biology at Western Sydney University, and he was a drummer in the Hummingbirds if you were getting around Sydney's pubs and clubs back in the day, the Trade Union Club, the Hopetoun Hotel, and you might even remember their big chart hit, Blush.